Hello everyone, today in this video we'll be discussing the fourth module of computer graphics. So as you can see, the fourth module is all about the theory concepts. Okay, just it's the theory concepts. Okay, so what will be our approach for this module is that we'll be going through the topics. How many topics are there? First we will go through those topics, and what happens when we go through the topics is we'll get to know what are the concepts we need to cover, so that whenever we cover each concept means we pick up this concept, and when we learn about that one, all we need to know is what did I learn from this one. Okay, after going through the whole concept, and before starting the concept you need to look in the notes how many pages that concept is. For example, if it is 2 pages, okay, so after going through the 2 pages in the theory, then you will come back to this list and you will see this is the topic I went through and what all I understood from that topic. In that way, if you study, you will be able to cope up with the theory things much faster. Okay, so that's the same approach which we will be following. We'll be going through each topic and coming back to this list and then summarizing what we understood from that topic. Okay, and along with that we'll also be seeing like what are the topics we need to focus more upon, because all the topics are not important, and some of the topics are much asked in exams. So we'll be going through the previous year papers to know what are the topics that are most frequently repeated and focusing more on that. So that will be our approach for the module 4, because this is a different approach than the previous modules, because this is about the theory concepts. So it will be much more beneficial if you go in this way. So let's get started, and if you like this video, hit the like button and don't forget to subscribe to my channel. So as you can see, this is the module 4, which has the concept 3D viewing and visible surface detection. What do you understand by the term 3D viewing? 3D viewing means there is a 3D object and you are seeing it. That's all what is 3D viewing is. If you are seeing from here, that is from this direction and from this direction and from this direction. So here we will be learning how to view the object in different directions and how it will look like in different directions and angles, and how do we project them in the screens. For example, if you have a cup like this, and if you look at from this way, it will look like just a cup like this with a line like this. If you look at this way, it will look like this, just as how I am seeing it right now, right? If you see it from this way, it will just look like a cup, because the handle is on the other side, it will not be visible. So that is a different viewing, means from the different perspectives you are viewing. Okay, so that's what the main idea of this module is, to give you brief information regarding what are the different projections you can see and how to display them on a screen. What are the different projections from different angles and how do you display them on a screen, and if you change the camera view, how the angle will be changing, and what are the things will be displaying, and what are the things that will be hidden, and how the size of the object changes as the object goes far and come back to the normal position. So that is what the 3D viewing is. Okay, and then we have the visible surface detection. For example, if I have a square like this, means a cube like this, okay, so I don't want to highlight the behind parts in this view, right? I just want to highlight what is here, what is here, what is here. I need not highlight these things and all, but if I highlight these things and these things also, everything will become confused and we will not be able to identify which is the front part, which is the back part. So always the back parts will be what? It will be invisible, because that will not be visible to us from the front side, right? Back side will be visible from the back side, right? That's common sense. And from the front side we'll be able to just see the front faces, what is visible. So it is very important for us to know what is the back side and what is the front side of the cube, so that we'll eliminate the things in that appropriate way. Okay, so that's what the 3D viewing and the visible surface detection things are. So let's go through the concepts now. 3D viewing concepts, 3D viewing pipeline, 3D viewing coordinate parameters. Let's divide the topics. So first, see how many topics are there. There are total 13 topics, and that's already divided into two parts here. Okay, it's divided into 2 parts. The first part is about the 3D viewing. Okay, the first part is about the 3D viewing, and the second part is visible surface detection. Okay, visible surface detection, few methods are there that's being specified here. We'll come back to this. First, let's see what are the 3D viewing. Totally 9 topics are there. Okay, so let's divide this into 3 points, and yeah, let's divide these 4 as same, because it's similar. Actually, these 3 are similar, and these 2 and these 4. Okay, so we'll be dividing this into these forms. So those are the groups in which we can divide the topics into, and then we'll be discussing them each one by one. Okay, so see, these are the topics, right? And the important questions which are expected from this module from exam point of view are the following. Explain 3D viewing concepts. Okay, the questions which are given in this document are like from each topic, what is the question type that might come. Okay, like 3D viewing concepts, just a question can come like explain 3D viewing concepts. Okay, then the second one, 3D viewing pipeline. So from each concept you need to know what does it mean. Okay, means what is 3D viewing concept, that you need to know and write in your own words. And what is 3D viewing pipeline? Write a short note on 3D viewing coordinate frames, projection transformations, and the orthogonal and the perspective projection. This important one. Okay, this is important. Explain the viewport transformation and 3D screen coordinates. Okay, OpenGL 3D viewing functions. So there are some functions in OpenGL that you have to describe here. Okay, visible surface detection methods and back face detection and depth buffer method. Okay, so these are the topics which we need to focus upon in this module. Okay, so let's discuss the let's go through the previous question papers as well to get a bit more depth analysis of what is the questions which are asked. So here are some of the question papers I have taken the screenshot of. So let's see what are the questions which are asked in module 4. So here is the one question which is what is 3D viewing, and with the help of a block diagram explain the 3D viewing pipeline architecture. So pipeline is asked once, and the transformation matrix for the orthogonal perspective projections, the topic which I told you differentiate between the orthogonal and perspective, right? So that is the important one. Depth buffer method, the last one, and the OpenGL visibility detection function, the last topics. Explain the steps for transformation from world to viewing coordinate system, the transformation matrix for perspective projection, and the OpenGL 3D functions. Explain the give the general classification of visible detection algorithm. Explain one algorithm in detail. Visible detection comes under the second half of the module. So in that the general classification means how many algorithms are there that you need to explain and that you need to list down and explain any one of them in detail. Okay, so that's what is there in the first question paper. Second question paper, the explain the two classification of visible surface detection algorithm. So two classifications are there which you have to explain, and explain with an example the depth buffer algorithm for visible surface detection. Also list the advantage and disadvantage of depth buffer algorithm. This was asked in the previous paper also, so it's important. Perspective and parallel, again important. Explain the OpenGL 3D viewing functions. So functions you need to know very well. What is projection reference point? Obtain the general special case perspective transformation equation. This comes under the perspective projections. Backface detection, second last topic. Explain the perspective projections again with respect to reference point, vanishing point with neat diagram, depth buffer, and how transformation from world coordinate to viewing coordinate is asked. Orthogonal projections in detail. The differentiation between the orthogonal perspective was there, right? In that orthogonal is asked here. Okay, and explain in detail the perspective projection. So here perspective is asked, depth buffer is there, and perspective projection for especially for frustum there are two types. This is the center frustum and this is the oblique frustum. So those two types you need to know. Visibility detection functions, OpenGL functions you need to know, and two classifications of visible surface detection, depth buffer, perspective and parallel projection, OpenGL 3D, and special case perspective back face. And yeah, those same questions are here. And 3D viewing and explain 3D viewing pipeline, OpenGL function, transformation matrix for orthogonal perspective, and world to viewing coordinates, and general classification of visible detection algorithm, OpenGL 3D viewing functions. And here also it's the same thing, OpenGL 3D functions and projection definitions, and visibility functions, perspective projection, depth buffer. So that's all what is there in the modules. So you got a brief overview of what is there in means what you need to focus upon, right? So let's get started with the topics. So let's start from the first topic. So these are all the topics which I had already mentioned. So let's get started with the first one, which is 3D viewing concepts. So what is 3D viewing concepts? Viewing an object in a 3D space is known as 3D viewing concepts. So what are the different concepts are there? To obtain a display of the three-dimensional world coordinate system, we first set up a coordinate reference or the camera parameters. We set up the camera and then we define the plane in which the 3D object is, then we capture it, right? And there are two methods. First is the parallel projection and second is the perspective projection. In parallel projection, all the object size are same because it will not depend on the distance between the size between the object and the viewer, but it will display as the object's original size is. Another method is the perspective projection, which will decrease if the distance is more, and it will be means the object will appear bigger if the distance is less, because as you move away from the object, the size of the object tends to look in our eyes like as decreased one, right? And depth queuing, so depth queuing means you can define the depth by using the wireframes like this. You can get to know easily if you see this diagram that it is a like this cube, right? Cone here and another cone attached here. So that is what a wireframe object is. And depth queuing, you can define the depth in it, means I can easily understand this is more nearer to me than these parts, right? Identifying visible lines and surfaces, so the visible line should be visible, means the front line should be visible and the back line should be non-visible, or it can be also shown as dashed lines. So if they ask about these things, you need to write about these things. Surface rendering, surface rendering means from where the light is coming, if it's transparent or opaque or smooth or rough, those things you need to define. Surface rendering. Exploded and cutaway views means the cross sectional view, like if this is the human brain, if you cut like this and show what is inside the brain, that's the exploded and cutaway views. Three-dimensional and stereoscopic viewing, here you will be using vibrations of the cathode ray tube, and you will be attaching a mirror. By that you will be getting the three-dimensional and the inner view of the object. So that's what the three-dimensional and stereoscopic viewing is. So what did you understand from the first topic is, if they ask you the question like explain the 3D viewing concepts, so what are the concepts you need to explain? First, 3D viewing means viewing an object in 3D means in 3D space, and you will be setting up the object here. You will be defining a plane, you will be capturing the object using a camera which is already defined, like where you will be keeping the camera. There are two methods of capturing, the parallel method and the perspective method. Depth is defined by the wireframing methods. And identifying the visible lines and surfaces, the front line should be visible, the back line should be dashed or invisible. Surface rendering, if the surface is transparent or opaque, smooth or rough. And exploded and cutaway views means the cross sectional views, and this is the stereoscopic views for looking what is inside the object. And that's all what is there in the first topic. So let's move on to the second topic, which is three-dimensional viewing pipeline. What do you mean by pipeline? Pipeline is just like a pipe, and inside that you will be doing something, so okay, that is known as pipeline. So what is the pipeline is, you will be going through different stages inside it, okay, means this is a pipe, you will be entering here and you will be outputting totally different, okay. So assume like for example, if you put here like ingredients for any food and the food comes here after going through different stages, that is what the viewing, that is what pipeline is, okay. And 3D viewing pipeline means an image will go, an object's image will go, and it will be coming out as a device image, like how it should be displayed in a device. This is how it will be displayed in the real world and how it will be displayed in a device. That transformation will happen in between many different stages are there. So let's discuss what are these stages. If you know what these stages are and what do these terms mean, you can write these whole things in your own words. And yeah, that's all. That will be the most important concept in the second topic, which is 3D viewing pipeline, okay. So let's discuss what are the different topics here and what do these topics mean. First is the modeling transformation. Modeling means you will be having, if you have different objects like a bottle here and a ball here, so bottle and the ball individually you will capture its size and all, that is known as modeling coordinates. So what are the individual sizes of these things? That is the model coordinates. World coordinate means what? WC means world coordinates, okay. World coordinate means what? You will combine this and then see what is the length and size of everything, that is the world coordinate. Then viewing transformation and the projection transformation, that is viewing it from the different angles, that is known as viewing and projection transformation. If you are viewing, it is viewing transformation. If it is projecting on a different surface, that is the projection transformation. Then we have the normalization and the clipping. Normalization means what? Setting up within a range, okay. For example, if you have a bucket which is of size 100 meters, very big bucket, but you want to display this bucket in a small screen, what you will do is, you will if it is 100 meter, you will consider this as 1 meter, and you will be displaying in a screen here of 1 meter, and here also you will be setting up the height also in the same way. So that is what the range, the standard range is -1 to 1. That transformation is known as normalized transformation. Then we have the last one, which is the viewport transformation, and then the device coordinates. Device coordinates means what? You will be able to see the 3D objects in a 2D plane, right? If this is the cube, I am drawing a cube here. This your phone is not 3D phone, right? But it is a 2D phone, which is a screen. But you can visualize a 3D object here, right? That's happening because of device coordinates. So a 3D object is getting displayed here, and an illusion is formed like you will be you are seeing the 3D object, but it's actually in a 2D plane. That is the device coordinates. So what will I mention now for each of these points? Just explain in your own words and give some relevant examples. That's what is there most important in the second topic, which is the three-dimensional viewing pipeline, okay. And third topic is three-dimensional viewing coordinate parameters. So what happens is, for example, here in this topic, what is the main concept is, this is the plane which is given to us here, and there is a point here. Okay, for example, if I have a solar radiation thing here, that in that way means that is tilted in some angle. Okay, it is not straight with the x-axis, y-axis or z-axis, so its normal coordinate will be coming up like this, like in a tilted way. So that's what the thing is about the viewing coordinate parameters. So how much it is aligned with the x-axis, y-axis and z-axis, that object, that is being discussed here. So the view plane normal parameters, so this is what I was talking about, the solar thing, it's coming in this way. And what is the angle with the x-axis, y-axis and z-axis? So if it is behind the z-axis, it is vp is less than 0, vp means viewing projection. If it is on the z-axis, it is equal to 0. If it is greater than z-axis, means far from the z-axis, it will be greater than 0. Okay, so like that for z-axis you can do for the x-axis also, x vp is greater equal to or less than 0, yp is greater equal to or less than 0. In that way you will get to know how much it is tilted and that object, how it actually looks like. So for example, here is a pyramid and this part of the pyramid is facing to sun, so its normal coordinate comes like this, and the y-axis, the x-axis and z-axis, each will be calculated how much it's aligned with the x, y and z axis. If I show you the picture, the view up vector, this is the input and this is the adjusted one. So this is the difference between the two. This is the actual input, this is the adjusted vector. Okay, that is the view up vector. So that's just in more means that is the main concept of the topic, which is 3D viewing coordinate parameters. So you will be defining the parameters to actually tell to the computer like how much it is aligned, what the object is present at that location, but how much it is aligned to the actual x, y and z axis, that you are specifying here. Okay, so UV and viewing coordinate reference frame. So we have the xy axis, right? In the opposite side we have the UV. Okay, here it will be having the UV and here it will be having the xy coordinate. So that's the same thing. If I show you the picture, this is the n coordinate, normal coordinate, and this is the v instead of y, and instead of x we have u. Okay, that's all the thing is regarding the UV. Everything will be same, just the values will become negative. Okay, so if you go through these topics, you will easily get to know what I mean. And generating three-dimensional viewing effects, if you place the camera here, how it should look like, if it placed here, how it should look like, if placed here, how it should look like. This will be defined by the vectors, okay, like the normal vectors. So by defining how much it is tilted, if you see in this direction, what will be the angle, if you see in this direction, the angle will change a bit. So the image means the view will also be changing, and from here also what is the angle, that will be calculated, and by using the vector value we will be able to see what is this, how the object will be viewed from this direction. Same thing goes for the whole 360 direction. That is known as 3D three-dimensional viewing effects. Okay, so the different angles, if you see, how will be the effects of viewing change. Okay, so that's all what is there in the third topic. So here's an example, as I already mentioned before also, about the cup. If you see from here, it will look like this. If you see from here, it will look like this. If you see from here, it will look like this. So it is already defined how each of these points it should look like. Just the execution of those points are happening. For example, if I want to look from here, the shape function where it is present, like from this view, how much it should be angle be visible, how much should be the light projection, those all will be defined, and the object will be displayed in that format. Okay, so that is there in the third topic, which is 3D coordinate parameters, three-dimensional viewing coordinate parameters. So you will be viewing from different directions and the vectors are defined. So to get an angle difference, how the object should be visible from different directions, and how should be the lighting also, it should be visible, that is also explained here. So if they ask the question in this topic, what I mentioned, that you have to write. Okay, so let's move on to the fourth topic, which is transformation from world to viewing coordinate. World coordinate, then the next topic is the viewing coordinate. From the world to viewing coordinate, how do we transform? Okay, so to convert the object from the world coordinate to the viewing coordinate, two things you have to do. Translate the viewing coordinate origin to the origin of viewing world coordinate system. Apply the rotations aligned in the x, y and z view axis with the world x, y and z axis. So first transform it into the world frame, and then again do the transformations like the x axis, y axis and z axis. Rotation or the translation, what you want to do, you have to do in the second means the final transformation, like the world position. Okay, so these are the formulas given. For the translation, you will do minus x naught, y naught and z naught, and for the rotation you will do the ux, uy and uz, vx, vy and vz, nx, ny and z. This u and v is just like x and y, and n is for z, So this is how we perform rotation in the world to viewing coordinate. Okay, these things you need to remember. If you multiply, what will be the result? In this video, I am just telling you what are the things, what do these things mean, but the memorization of these things is totally upon you. Okay, so you have to memorize these things, however, in the way you feel it is beneficial for you. Okay, so these are the formulas which you need to keep in mind if they ask the question in under this topic, like how do you transform from world to viewing coordinates. What are the things you need to mention is, first you will make the frame of the viewing to world coordinate here, apply the rotation or whatever you want to apply, and write these matrices values here and explain what are those terms mean. If you apply it in a composite way, means both these things together, this will be the matrix. And finally you can have some equations here. Matrix element are evaluated as follows for the u, v and n values. Okay, so that's all what you need to mention from the world to viewing coordinates. This question was asked in previous paper. I have already discussed in the starting of this video. I already showed you also this question was asked, so make sure you have mentioned these points in the exam means answer sheet. Okay, so let's move on to the fifth topic, which is projection transformations. So before moving on to this topic, let me tell you that the first 1/3 of this module is over. So in the 1/3 of the module we discuss these things, right? The 4 topics we have done. Next 3 topics we will do in this way, and then we will be doing these things. Okay, then the first half of the module will be over. So in this, the projection transformation, orthogonal perspective. Okay, in one sentence only I will explain you what is orthogonal and what is perspective. Orthogonal means what? If you have a cube like this and you are able to see the cube's same dimensions from a different direction also, means from the different distance also you are able to see in this way, that is known as the orthogonal projection. Means orthogonal means 90 degree. Perpendicular projection, there will be no decrementing in the size as the distance changes. But in perspective viewing, what happens is, if this is the object here, at that time if you go far away from the object, it will become like this, and at one point it will become one point only. So if you see from here, the object will be very small, and if you see from here, it will be relatively big, and if you see from here, that's the original size of the object. This is known as perspective, and the last and the previous one which I mentioned is the orthogonal. Okay, so that's what we will be studying now, how to make the transformations and what are the matrix values to use to display it in the appropriate manner. Okay, like the orthogonal or the perspective. So let's go to topic 4.5 and discuss what is there, and if they ask in exam what all you need to keep in mind and mention in the answer sheet, that we will be discussing now. So projection transformation, what is the projection transformation? The projection different ways, that is known as projection transformation. So how many ways are there? There are 2 ways, parallel or orthogonal, both are the same thing, and the perspective. Parallel means it will preserve the coordinates values and the size of the object, it will look like the same as the original size, but the perspective means it will change based on your perspective. If you see from far, it will be small, if you see from near, it will be larger comparatively. Okay, so that's all what is there in the first topic, which is the projection transformations. So here's the diagram given. If you want, you can make this diagram as well. This is the parallel view, and this is the projection view, perspective view. Okay, here's the bigger object, but as you move on, it will become smaller. That is the perspective. So just a brief information is given regarding these two. Now we will dive into depth regarding these 2 topics in the upcoming 2 topics. So here is the orthogonal projection. So note it down what all you need to keep in mind while answering this question. So first you need to explain what is orthogonal projection. That means the parallel lines will be there and the object size will be preserved. Object size will be preserved is a key point in this answer sheet. Okay, object size will be preserved. That's the main difference between orthogonal and the perspective. So here you have to draw this diagram. This is the object, and from this view you can see in this way, from this view you can see in this way, from the top you can see in this way. This is known as plane, and these both are known as elevation. That is the second point you need to mention. And the third point is axonometric and isometric orthogonal projections. See here you just can see one side of the cube, right? But here in the same 2D plane you can see multiple faces, this face, and this face. Seeing of the multiple faces in the same plane, that is known as axonometric and the isometric orthogonal projections. Okay, that you need to keep in mind. And orthogonal projection coordinates, see there is no point in having the transformation things and all, because the values are trivial. Values are trivial means if you have 2 parallel lines, here also the distance will be same between these 2 points, here also the distance will be same in between these 2 points. So there is no point in considering the transformation equation, because it will be same only here, both will be same only. So why you need to transform the object? But in perspective it will change, right? So that's why you need to transform and make it to the original size. So that will be discussed in the second topic, but here there will be no transformations. In orthogonal there will be no transformations. Okay, keep in mind. And clipping window, orthogonal projection volume. How do we clip the window? So suppose that I want to display a rectangle. I'll not be specifying all these points, I'll be just specifying these 2 points, the bottom left and the top right point. If I specify these 2 points, the triangle will be made automatically, and this is how you clip the picture in a bigger plane. Okay, just the y, x, w max, w means the world coordinates, max values and the min values, that will be specified, and this is the clipping window defined. Okay, so that's what you need to mention in the clipping window. Orthogonal projection view volume. So this is the orthogonal projection view volume. From the side view it will look like this clipping window, from the top it will look just a single line. Okay, and this is the this also you need to mention, like this is the clipping window, then this is the near plane, and this is the far plane. So this is known as orthogonal projection view volume. This volume is known as orthogonal projection view volume. Okay, this cuboid. So here is the far plane between, and this is the near plane. Between these two is the orthogonal projection view volume. So if they ask you what is that, you have to mention that it is a rectangular parallel piped. Parallel piped means it is in this way, and this is a clipping window. Okay, so the volume in between these two is known as the orthogonal projection view volume. Then finally we have the last topic, which is the normalization transformation for an orthogonal projection. Normalization means what? If you have like an elephant here, elephant is very big, but if you want to see the video of elephant in your phone, you will not say someone to build a phone as big as the elephant, right? You will be capturing that elephant in a small device. That is known as normalization. Means this whole ratio will be converted, and specifically it will be displayed. That is known as the ratio transformation or the normalization. Same thing happens here also. We will be transforming this object's coordinates here in a smaller size, and the display window, that is known as the normalization. So here are some matrix values you need to memorize and write in exam. So this depends upon you how you memorize. So I just told you what are the things, it's upon you to memorize. Okay, so if you normalize this, this will be a bigger object, it will be normalized to a smaller object between the values minus 1 and plus 1. Okay, so this was about the orthogonal projection. What if I wrap up, what are the things you need to keep in mind if they ask you in exam? You need to mention what is orthogonal projection. There will be normal vectors, and the parallel lines will be there. Object size will be preserved. Object size will be what? Preserved. And these are the different views, elevation views, and this is the plan view, this is the top and the front rear views. And here you will be seeing multiple faces, that is known as axonometric or isometric orthogonal projections. And here the projection coordinates are there. Since between two parallel lines the distance is same, so it will be trivial, and you need not have transformation equations for it. And clipping window is defined between 2 points, x min, y min, and x max, y max. And here is the clipping window from different directions. This from the side view and this from the top view. And the volume of the projection is this one, between the near plane and the far plane of the clipping window. What is the volume point of the rectangular parallel pipe? That is known as the orthogonal projection view volume. Normalization means bigger picture into a smaller device. You will be able to see by using the ratios. It should be between -1, -1 to +1. Next, finally draw this diagram and write this matrix values. Okay, same thing goes for the next one also, the perspective projection, but here there are some few more concepts more than the orthogonal projection, but I'll tell you what you need to focus upon, and just remember whatever I tell you to remember. Okay, because that's what the relevant is. No need to remember all the things, just what I tell you, remember that, and write the same in the exam. Okay, so in the perspective projection also, you understood the meaning of perspective, right? If you go away from, if you give your friend to take a photo, you're standing here, and you take your give a friend to take a photo here. If you go far away from you from the camera, you will be appearing small in the photo. If you stay means near to your friend, you will be looking bigger in the camera, right? So that's what the perspective projection is. That same thing happens in the real world camera also. So that is known as perspective projection. Object size will not be preserved. Object size will not be preserved, the main key point of the perspective projection. Okay, so here's the diagram. If you want, you can make this diagram to explain more, and it will look like if you had written more. Like if you include diagrams more in your answer sheet, it will look like you have written more, and you might get more marks as well. Okay, perspective projection transformation coordinates. So see, since the transformation is required here because the size changes, so we'll be looking what are the transformations present here. These three equations pakka you memorize. Okay, so it's very easy to memorize. I'll tell you how to memorize. X, y, and z you are doing, so x dash, y dash, and z dash, and you tell me what is 0. 0 means x minus x, y minus y, and z minus z. All these three will give what? 0. So just write here x minus x, y minus y, z minus z, and after that copy paste this one here, except the dash you write here PRP, 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 PRP. Finally you write u here. Okay, again xyz you are finding, so you have written xyz here. What is 0? X minus x, y minus y, z minus z, and copy paste the same thing here, prp, 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 and u. Okay, these are the equations which describe the perspective projection line in parametric form. This is one equation you need to mention in the answer sheet. And what are the next equation is the special cases. Okay, special case is very important. This is upon you. If you want to skip, if you want, you can skip this, or you can write this as well. Okay, because this is also important, but this is more important. Okay, so whatever you can memorize and write in answer sheet, that will be beneficial for your means you can get more marks. Okay, so this is very important. Special cases is very important. You have to mention this for sure. Okay, if they ask perspective projection, never miss this one, which is special cases. I'll be telling you what is these things, how to remember this, and yeah, that's all. How to memorize this, and what is this, how to memorize this. Okay, so there are how many cases? Total 4 cases you have to mention. In the first case, z is equal to 0, and the second case, all the values are 0. First, what? Z is 0, and sorry, not z is 0, along the z axis, then along the coordinate, and along the uv plane without z, and along the uv plane with z. Okay, these are the 4 cases. Along z, 0 0 0 the coordinates origin, and uv without z and uv with z. Okay, these are the things you need to remember. There are 4 cases here. Now if you observe carefully, you need to write 1 or 2 times, then only it will be present in your mind. Okay, make sure you write 1 or 2 times very slowly. Okay, focus and write very slowly, it will stay in your mind. Okay, so see here what is the thing we are trying to find out. xp and yp are trying to find out in all the cases. Here also we are trying to find out what? xp and yp. Here also we are trying to find out what? xp and yp. The last one also we are trying to find out xp and yp. So if they ask you the special cases, firstly you have to write xp and yp. Write as along z axis, and then start with xp is equal to yp is equal to, just write it and leave it. Okay, then what you have to remember is, only remember this one. From this you will be deriving the 4 cases based on the context. So see here, zprp minus zvp, zprp minus z. You got in mind, right? zprp minus zvp, zprp minus z. That's all. Here also write the same thing, zprp minus zvp, zprp minus z. That's all. If you remember this formula, you can easily write the 4 formulas. So remember right now, zprp minus zvp, zprp minus z. Here also you write the same thing. It's for x, you write here x. If it's for y, you write here y. That's the first case, which is z axis. Okay, along the z axis. Then the next one is along the coordinates. So in coordinates, what you will do, you will just consider the second half of it. zvp by z, right here. zvp by z, the same thing we will be writing here here also. And y is y, so x is x. That's all we want to write here. After writing the first 2 cases, you are supposed to go to the 4th case, not the 3rd case. You are supposed to go with what? 4th case. Okay, not the 3rd case. In the 4th case, what you are supposed to do is just consider this part. Blink your eyes to take a screenshot in your mind. Okay, so I usually do that. If I blink my eyes like this, it will stay in my mind. That screenshot will be stored. So you just have to write this much in the 4th case. Okay, this much you have to write in the 4th case. Okay, so this all what you have to write in the 4th case. Don't write zvp. Okay, so if I show you the 4th case, this is as follows: zprp by zprp minus z, zprp by zprp minus z, and y is for y, x is for x. After that, finally you will come to the case 3, which is uv with without x, and here you have uv with x. Okay, so uv without x, what you will be writing is just the same equation you will be writing here also, but then you will be separating these 2 things. Okay, you will be just separating these 2 things with the denominator. Means zprp by z you will be taking separate, minus zvp by zprp minus z. You are just separating these 2 terms with the respective numerator. After you have separated these 2 things, this is close with this first one, you will make it with this one only. Same thing goes for y also. It will be with the first term, this term with x, and this term what will have, the same thing will have x only. Write 2 times x, just add prp. That's all. Just add prp. Take the prp from here, add it here. The prp will actually not be there. It will be vp. Just make it as prp. That's all. If you observe carefully, you will easily get the pattern and keep in mind. So make sure you memorize these cases in any way you want. This was my way of memorizing, so you can use anywhere to memorize, but make sure you memorize and note this, means write this special cases if they ask you about the perspective projection. Okay, just surely marks for it. So after these things, we have a few more concepts in the perspective projection. So I'll be just going through briefly what are the concepts mentioned there, and there are many matrix values and the equations. Even I haven't gone through it as of now. So I'll just give you the brief overview of what it is, and how much you can remember, that's better for you. Okay, but the basic thing is you need to know what it is, right? That's more important. So yeah, here also you can make this diagram to fill the answer sheet. So here what you have is the clipping window and the projection reference point here. If it is far, it will be in this way. If it is like very far, it will be like looking like a parallel line. This also make sure you make, so you can get like some content is there, ma'am will think like that. Okay, so vanishing point. Okay, next one is vanishing point. Vanishing point means what? This is the diagram here. If you go very far from the plane, it will look like a small dot. That is known as vanishing point. Also it is known as projection reference frame. Okay, both are the same things. And yeah, this is the projection reference point, and this is the clipping window, and this is the near clipping plane. And since in the previous one it was rectangular parallel pipe, right? But since here it is like merging to the same point, it will not be a rectangular parallel pipe, but it will be rectangular frustum, and the volume formed in between the near plane and the far clipping plane is the rectangular frustum view volume. Okay, for now just focus on the key concepts. I'll be again revising the concepts after the end of this topic, as we have been doing for each topic. So you need not worry about what you need to keep in mind, just understand the concept now. Okay, so this is what the rectangular frustum view volume is. Now there can be two types of frustum, which can be center line frustum and the oblique frustum. Okay, that's one of the things you need to mention. Perspective, projection, transformation matrix, these are the values. It's upon you how you memorize these things, but you memorize this and write how much ever you can in the exam. Okay, symmetric perspective projection frustum, this is what I will be explaining now. Okay, so here there are two types of frustum. As you can see, this is the symmetric frustum. There is a center point here, center line, but here and second one, this is the oblique one. Okay, it is stretched somewhat to the right side, right? These are two types of frustum which I have to explain, and that marks the end of this topic. But before that, normalization will be there, the same as the previous one we have explained. As I explained in the previous one, orthogonal normalization, the same normalization is here as well. Okay, so that's all what is there in the perspective projection. So let's again revise what is there and what I need to keep in mind. Okay, so as starting from the same as the orthogonal projection, will be first defining what is the meaning of perspective projection. The size will not be reserved. As you move away from the project, away from the object, the size will be decreased, and as it decreases, it will come to a point, it will be vanishing point, that is also known as project reference point. So here only you got 3 points. What is perspective projection, and what is the projection reference point, and what is the vanishing point. So 3 points you have mentioned here itself. Then you will be doing the transformation also, because the size is changing, that's another point. And these are the equations you need to write. After that, the special case is also there, which you need to write, very important. You need to make sure you write this in the answer sheet. And after that, what we have is the this is explained, and you need to explain what is the near clipping plane and the far clipping plane. In between them, rectangular frustum view volume is there, that also you need to explain. And perspective, projection, transformation matrix. This transformation matrix, if you can remember, else you can, means if you don't remember, what can you do, just leave it. Okay, so that's all. And here is the symmetric perspective projection frustum. Two types are there, the symmetric one and the oblique one. Okay, symmetric one, this is the symmetric one, and these are the values which you are supposed to write in exam, but it's actually very hard to memorize the values, right? I don't know what to do. Here is the oblique one, so I just know the meaning between these two. The values I really don't know how to write. There are many equations here, so whatever you can memorize and write, that will be better for you. And this is the normalization. Explain your own words what is the meaning of normalization, and why do we need normalization, and how the object will be before normalization, after normalization, how it will be. Okay, that's all what you need to write here, and some matrix values are there, and include that as well in your answer sheet. So that is there in the second, means 3 parts were there, right? We divided the whole syllabus. Let's go back to the syllabus here. Syllabus we divided into 3 parts, right? The first half of the syllabus was divided into 3 parts here. The 2 parts are what? Over. Okay, so this were the division. The first part was over. Now second part is over. We'll be seeing the third part. It's just the viewport transformation and the viewing function. So let's quickly discuss what is in the third part of the first half of module. Okay, so where does it start from? Yeah, here it starts from the viewport transformation, 3D dimensional screen coordinates. So how is the screen coordinates in a 3 dimension? That matrix is specified here. Okay, for x, y and z, and this for the h coordinate. Okay, And yeah, that's all what is there in the viewport transformation 3D dimensional screen. For the Z, you'll be having a depth also, which is known as H. So that's all what you need to explain. Write some few words about what is 3D, how many dimensions will be there, what are the different dimensions and values for each of these planes. So like those things you have to write here, and this is the matrix value. If you can remember, you can remember and write. And after that we have the OpenGL 3D viewing function. So if they ask you about the viewing functions, what I need to write? See, at the start of the video I showed you the question papers, how many times the OpenGL viewing functions were asked. So it's very important. So what are the different categories of the viewing function? The categories of viewing function is viewing transformation function. In that we have matrix mode and look at. Okay. And in OpenGL orthogonal projection we have the matrix mode and GL ortho, and in the perspective projection we have the GL frustum, and in the viewport and display window we have the viewport. And here's an example. If they ask the program also, that's what you need to write, but I don't think the program was asked, just the function definitions and the means what does the function do and its parameters and all those things were asked, right? So you need not worry about the program here. Okay, so that was there in the first half of the module. Okay, so let's move on to the second half, which is the visible surface detection method. Let's go through the syllabus here. What are the things present in the visible surface detection methods? Visible surface, what do you understand? Visible surface means what the surface is visible, that is visible surface. Detection means detecting what surface is visible. Methods means the way to do. The way to detect what surface is visible to our human eyes is known as visible surface detection methods. There is a method A. If I use this method A, I will get to know this is visible to humans from the front view, this is also visible, and this is also visible. The back three, which is this one and this one, this is not visible. This categorization of the visibility faces, that is done by this method, and this method is known as surface detection method, visible surface detection method. So how many things are there? The first thing is classification of visible surface detection algorithms. Classification, see in the question paper you yourself saw from your eyes that how many times this was asked, right? So this is very important. Classification, I guess there are two classifications and that will be discussing now. Backface detection, depth buffer method, very important. OpenGL visibility detection functions. So this function is same as this one, like how we discussed, just the parameters will be different, the logic will be different, but you need to know what are the important things you need to keep in mind. Okay, just memorize few functions which can be used both here and here, that will be more beneficial, right? So classification first we will discuss, and two algorithms, and second one is more important. So if you do this much, you are good to go, you are done with module 4. Okay, so let's get started and quickly finish the module 4. So here's the visible surface detection methods. Classification, there are two classifications. We can broadly classify the visible surface detection algorithm according to whether they deal with object definition or with their projected images. See, if a doll is here, that doll is known as object, and the doll is, if the shadow of the doll is on the wall, that is the projected image of the doll, right? So these are the two things. Remember this example, the doll and the shadow of the doll. The doll is the object and the shadow of the doll is the projected image. Or if you take a photo of the doll, the photo is the projected image, means whatever the light comes here, that is getting projected in the camera and that is getting captured and saved, right? So those are the two classification of the visible detection, visible surface detection algorithm. So see, this very simple, but it's asked much in the exam, so make sure you don't miss this one. Okay, so object space methods. So two types of methods are there for detecting the object space and for detecting the image space. Okay, so two things are there. For these two, separate algorithms will be there. Okay, so backface detection. So how is the backface detection happening? So what is a backface? So yeah, here only the picture is there, right? Can explain it here only. Okay, so it's not actually there. So this is the equation. Okay, this also we are discussed, I guess, in module 2. Ax plus by plus c plus d is less than 0, then it is behind the plane. If it is equal to 0, it's on the plane. If it is if it is greater than 0, it is in front of the plane. So if this is the cube here, less than 0 means these values. If it's less than 0, the point is this one. If it is equal to 0, means it's in any of these surfaces. If it is greater than 0, means it is means in front of the plane. Okay, so that's all. The backface detection, we will be using this test and applying the values and checking a of xyz is behind the plane or on the plane or in front of the plane. That is known as the backface detection algorithm. Okay, so that's what mainly it is there, and you can go through the details of it to get more information, but that's what the upper picture is. Okay, depth buffer method, this is a very important one. What is depth buffer method? What is depth? Depth means how much deep it is, how much deep the object is, right? What is the depth of this one means, if it is very thick, at that time it will be very light here, and as it goes depth in the depth deeper it will become very dark, right? So that is the thing which you need to set in the objects as well. How much far is the object, in that way the light effects will be faded and it will change the colors. So that's why we need the depth buffer method. Buffer means it is an array or the cache which will store the values of in this depth what is the color, in this depth what is the color, and so on. Now here is a perspective of an object rotating. What is the part of the object that will be visible, that's getting shown here. Okay, so make sure you very well go through this algorithm, and you need to know what is the depth, as I just explained you, that's known as the depth buffer, and why it is used, and what are the different key points regarding that you need to know. Okay, and depth buffer algorithm, this you need to know very well. Okay, and you need to write the same algorithm. So let's go through it very quickly. What is the depth buffer algorithm? So in depth buffer algorithm, initialize the depth buffer and the frame buffer, so that for all buffer position x, y, depth buffer is equal to 1. Initially depth buffer is equal to 1, and the frame buffer is equal to background color. Frame buffer means what is visible to us. Depth is what is inside the object. Okay, that is 1 first. The depth is 1 and the background color is initially set. Process each polygon in a scene one at a time as follows. Each polygon will be considering one at a time, and calculate the depth if not already known. We have to calculate the depth of it. How do we calculate the depth? We have a formula for that. Using that formula we will be calculating the depth. Okay, after that we will be applying that depth value z. Z is the depth value which I calculated to the depth buffer. After that we will be setting the frame buffer to the surface color. If that much is the depth, what will be the surface color, that also we will calculate and store it in the frame buffer. So this is the formula which by using which we will be calculating the depth at the surface, and in the depth position xy you will be using this formula. Okay, make sure you memorize this formula. This you can't skip. Okay, other things which I told you, matrix values and all, that you might skip, but this is very important. This is a part of the algorithm, so you should not skip this one. Okay, otherwise the marks will be cut. Okay, so here is some constants here, and you will be using the scanner algorithm to find out the depth and the distances. You will be using slope values and all. So that's all what is mainly in the top overview of these things. So you can go through it in the depth for more information. And yeah, that's all what is there. You will be just calculating the depth regarding by using the slope values, and you'll be using the depth buffer and the z values, how much is the depth. Based on that you will be calculating the surface value, how much surface intensity should be there based on the depth. Okay, you see, if you see in the ocean, at that time if the ocean is very deep, at that time in the top you will be seeing very dark color. But if the ocean is just this much, you will be seeing literally what is present here. If your coin is present here, you will be able to see your coin which is dropped in the pool, right? So that's what the depth is. This is the depth, and based on the depth the surface values will also change. How much should be visible, how much should not be visible, that will also change. Based on these formulas we will calculate that for each face and for each projection. Means if the polygon is moving in this way from here to here, then here to here, what are the angles getting changed, what are the rotations happening. Based on that the surface values should also change, and the depth values visibility should also be changed, right? If you have a box like this and that box gets rotated here, this is the depth value of the box. But if the box gets rotated in this way, this will come in the top surface and this will come in the back surface. So those changes should also happen, and for that we will be using the depth buffer algorithm. Okay, so that's all what is there in the depth buffer algorithm. And coming to the last topic, which is about the visibility detection functions, we have the polygon culling function. So back face removal function is there, which is defined here. You can enable or disable it. And depth buffer equations, glut init display, glut clear, enable and disable. And to enable the buffer definitions, we will be using the depth also here, and that is the function we already discussed in the lab part, right? This is the fourth program, I guess. GL clear depth, and the depth range can be set, and the depth function can test the condition if it is less or greater or equal to what depth values you have given. Depth mask, we can mask the depth value either to true or false. And OpenGL wireframe surface visibility methods, what is solid and what is wireframe. If this is the box which I have, if it is colorful, it is known as solid. If it is not colorful but it has some wires here, and that wires can also give us some information regarding if it is more deeper or not. For example, if I show you a diagram here, I have a wire like this. Okay, as you can already see, like this is a object which is more depth here, right? By using wireframes, but it just have a solid color. Solid color will be like full solid color, you can't identify it. That's one of the advantages of wireframes. To identify the depth we can use. How we can use this exactly, like for example, if you have it in this way, you will be calculating the angle change here and the slope here. So you will get to know how much depth it has come, what is the peak height of it. You can make a 90-degree angle here with this surface and calculate what is the distance here, means how much deep it is, that you can calculate, right. So that's why we use the wireframe surface visibility methods, and these are the functions and the syntaxes for it. Okay. OpenGL depth queuing function is also the same thing. Enable fog if fog I is just the means integer, or f is the float values, and GL fog is set to GL fog function to set an atmosphere color that is to be combined with the color of object after applying the linear depth queuing function. Depth queuing means in the depth what color should be visible. If it is a blue pot, it will be like dark blue at the end, right. If it is a yellow pot, dark yellow will be at the end. So like that only what should be displayed, that we are specifying the atmosphere color using the GL fog f functions. Okay. And what else we have, this is the very important one, this difference between perspective projection and parallel projections. So here are some of the things which you need to focus upon. So the main thing which you need to focus upon is no change in the size of object in the orthogonal parallel projection. Here the size of the object is inversely proportional to the distance. More the distance, the smaller the object. The lesser the distance, the bigger the object. Okay. So here some more few key points, you can go through it. So yeah, that's all what is there in the module 4, and thank you so much for watching. I'll see you in the next one.